Hello everyone, my name is Tony Rodriguez and today I'll be presenting on modular arithmetic. So here's a quick overview. What is 100 modulus 9? So that seems pretty easy. 100 modulus 9 equals 1. We can look at this question as what is the remainder of 100 divided by 9? So let's look at what is 189 divided by, modulus 18. So we know that 180 is divisible by 18, so we can go 189 minus 180 equals 9. So here's a book problem I'd like to look at. The book problem says, if one person says they can write a number n in the form 5a plus b, where a and b are integers, with b being greater than or equal to 0, but being less than or equal to 4, and another person says they can write the same number in the form 5c plus d, where c and d are integers, with d being greater than or equal to 0, but being less than or equal to 4. Show that b equals d and a equals c. So here's my proof that I filled in. So I have, we let a, b, c, and d be given such that 5a plus b equals 5c plus d, with b being greater than or equal to 0, but being less than or equal to 4, and d being greater than or equal to 0, but being less than or equal to 4. Since this can be rewritten as 5 times a minus c equals d minus b is divisible by 5. But d minus b is greater than or equal to 0 and less than or equal to 0. And 0 is the only number in this interval that is divisible by 5, so we can conclude that b equals d. From this it follows that 5 times a minus c equals 0 because 5 times a minus c equals d minus b, which equals 0, from which it would follow that a equals c as well. So here's another book problem. They're using the same formula, which is k plus b to represent any number. So for this proof, I wrote down, let a, b, and c and d be given such that 7a plus b equals 7c plus d, with b being greater than or equal to 0, but being less than or equal to 6, and d being greater than or equal to 0, but being less than or equal to 6. We can also rewrite this one as 7 times a minus c equals d minus b. D minus b is divisible by 7, but d minus b is greater than or equal to 0, but less than or equal to 0. So, and 0 is the only number in this interval again that is divisible by 7, so we can conclude that b equals d. From this it follows that 7 times a minus c equals 0 because 7 times a minus c equals d minus b, which equals 0. From which it would follow that a equals c as well for this one. So what is the significance of a equaling c and d equaling b? So since a equals c and d equals b, this also proves that there is only one way of representing a number in the form ka plus b. So why is ka plus b significant? The form k plus b is also known as the division theorem. The division theorem is any number n equals k plus b, where b is greater than or equal to 0 but less than k. So in this case, n is a dividend, k is known as a divisor, a is known as a quotient, b is also the result of n modulus k, and b is also known as a remainder. So what is the division theorem? The division theorem tells us that for two integers a and b where b is not equal to 0, there always exist unique integers q and r such that a equals q times b plus r, and where r is greater than or equal to 0 but less than b. So for example, let's say we have a equals 17, b equals 3. We can find q equals 5 and our remainder equals 2. So that 17 equals 3 times 5 plus 2. If r equals 0, then we say b divides a, or a is divisible by b. This establishes a natural congruence relation on the integers. For a positive integer n, two integers a and b are said to be congruent modulo n, or a is congruent to b modulo n. If a and b have the same remainder when divided by n, or equivalently if a minus b is divisible by n, it can be expressed as a is congruent to b modulus n, where n is called the modulus. So here's some basic examples. Two things to remember are two odd numbers are congruent to modulo 2 because all odd numbers can be written as 2n plus 1. Similarly, two even numbers are congruent modulo 2 because all even numbers can be written as 2n plus 0. So let's look at these three. Let's look at these three that I've listed here. So we say 38 is congruent to 23 modulus 15 because 38 equals 15 times 2 plus 8, and 23 equals 15 plus 8, which in these two cases the two remainders are the same. So 8 is congruent to 3 modulus 5 because 8 equals 5 plus 3, and 3 equals 0 times 5 plus 3. As you can see, those remainders are the same. In this other case, however, we have 8 is not congruent to negative 8 modulus 5 because 8 equals 5 plus 3, and negative 8 equals negative 2 times 5 plus 2. So as you can see, the two remainders are different. In one case we have 3, in the other we have 2. So why is the division algorithm significant? So we can actually use the division algorithm to convert any number to base whatever. It could be octal, binary, or hex. It doesn't matter. For example, the form for converting a number to binary would be n equals 2 times a plus b, where 2 is our divisor or our base, a is our quotient, b is our remainder, and n is our dividend. So the algorithm consists of these steps. So we take n modulus 2 to get our b, or remainder, formulating an a, our quotient, to make the statement true, subtracting our remainder from n, and then we're dividing our n, our dividend, by 2, our divisor, to get our new n. So we repeat these steps until n becomes roughly 1. While writing the remainders are b's right to left. A small program using an online Java compiler that I decided to make to show the division algorithm in action. So in this case, we created a method that converts a number to binary, a base 10 number. So here I have all of my respective n, k, a, and b, with our k set to 2 for our base. So while n is greater, so we have a while loop while n is greater than 0. So what we're gonna do is we're gonna calculate our remainder here, n modulus 2. And then we're calculating our quotient here, which is n minus b. And then here we're subtracting our remainder from our number, and then we're dividing our number by our divisor. So let's enter a few numbers to get them converted to binary. So let's try 43. So as you can see, here are all the steps. So our remainders are the ones that we're looking at. So we're writing our remainders right to left. So in this case, we'd have 1 here, 1, 1 again, 1 again. Our 0, 0, 1, 1, 0, 0, 1. Let's try another number. So here we have all of our remainders right here. So bit 1 would be 0, bit 2 would be 0, bit 1 would be 1. As you can see, they correspond with our number in binary. So just to prove that this algorithm works with any base number, here we have the representation of 305 converted into hex. So we have our remainders here, which are 131. So 305 in base 16 is 131. So we want, and then we have 77. So here we have our remainders. 13 corresponds to D in hex. So we have D4, or 4D actually, right to left. And then we have examples in octal. Here we have we're representing 33. So we have our remainders 1 and 4, which are written right to left, or 41. So 33 in octal is 41. Here we're representing 75. We have our remainders 3, 1, 1. Written right to left would be 113. So 75 in octal is 113. Well, that is all I have for you guys. I hope you guys found this really interesting, and I hope that new way of converting any number to any base makes things a bit easier when converting numbers to binary or hex or octal. But yeah, thank you.